Hello and welcome to my YouTube channel called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. This video is part one of a two-video pair. This one explains general concepts and principles of control charts. The part 2 video describes several different kinds of control charts and which to use when. As usual in the book and in these videos, we'll start by going quickly through a list of keys to understanding, or KTUs. This will give you the overall picture of the concept on a single page. After that, we'll go into a detailed description of each of the keys. For this video, there are 5 keys to understanding. The first key says, all processes have variation. A process can be said to be under control, stable, or predictable if the variation is confined within a defined range and the variation is random, that is, the variation shows no pattern. KTU number 2 says, such variation is called common cause variation. It is random noise within a process which is under control. Variation which is not common cause is called special cause variation. It is a signal that factors outside the process are affecting it. Key number 3 says, any special cause variation must be eliminated before one can attempt to narrow the range of common cause variation. Key to understanding number 4 says, control charts show variation in a time sequence from left to right. Control charts tell us whether the variation is within the prescribed range for common cause variation, and run rules define whether the variation is random or whether there is a pattern, which is also visible on a control chart. The fifth and final key to understanding says, data are collected in a number of rational subgroups of size n greater than or equal to 4, under essentially the same conditions. And here on one page are all 5 keys to understanding the concepts in our part 1 video on control charts. You may wish to pause the video at this point and read them all together. When you resume the video, we will go into detail on each of these keys. Okay, now let's take a closer look at each key to understanding. KTU number 1 starts out by saying, all processes have variation. In much of statistics, the universe of data is from a population. For example, a sample of voters polled prior to an election. Control charts are used with a different kind of statistics. In this kind, populations are not used. Instead, the universe of data is made up of measurements or counts from a specific process. It may be, for example, a manufacturing process which is comprised of a number of steps used to assemble a product. Usually, a count or a measurement can be taken at a number of steps in the process. Almost none of these counts or variations or measurements will remain absolutely constant over time. There will be variation. We can't avoid variation in real-life processes. All processes have variation, but we do want some limits on it. KTU number 1 goes on to say a process can be said to be under control or stable or predictable if the variation is, number 1, confined within a defined range and is, number 2, random, that it shows no pattern. Each black square on this control chart is a measurement or count taken during the execution of a process. With the exception of one outlier above the upper line, all the points are confined within a range defined by these 2 dotted lines. These dotted lines are the upper control limit, UCL, and the lower control limit LCL. Because of that one outlier, this chart shows that the process is not under control. We need to find out what happened to cause that outlier. And in addition to being within a defined range, any variation must not show a pattern. It must be random. In this chart, there is no repeating pattern. The variation is random. So this process does not meet the first requirement to be called under control. All of its data points are not confined within a defined range. There is that outlier above the dotted line. However, just eyeballing it, it does seem to meet the second requirement, that is, the variation is random. There is no discernible repeating pattern. If the variation in our process is, as described in KTU number 1, that it is random and it is within a defined range, we call that kind of variation common cause variation. This kind of variation is like random noise within an under control process. If we have this kind of variation, then we can be comfortable that the process itself is consistent. And we can be comfortable in predicting that the process will continue to vary in a random fashion within that range. Predictability is very important in process management as well as for customer satisfaction. If we don't limit variation to a predictable range, we can't plan. We can't plan our expenses, our revenues, or our purchases, our hours, and so on. And a customer who buys a quarter-pounder hamburger may not notice if they get 0.24 or 0.26 pounds of meat instead of 0.25 exactly. But they will probably be dissatisfied with 0.18 pounds, even if the average has been 0.25. Customers feel variation. They do not feel averages. Here's a compare and contrast table for common cause variation and special cause variation. Common cause variation is expected, but special cause variation is unexpected. Common cause variation is like random noise, while special cause variation is a signal that something is different outside the process or it has changed. Common cause variation is part of the process, while special cause variation is outside the process. Common cause variation occurs within a consistent range of values and has no pattern. With special cause variation, some data points occur outside that range, or there is a pattern. As an example, an inspector timed one step in a manufacturing process 10 times. The times it took were 21, 19, 18, 20, 22, 20, 18, 19, 22, and 20 seconds. These were all within a range of 18 to 22 seconds. But when it takes 26 seconds or more on some occasions, that is an outlier. And an outlier indicates that there is something inconsistent that has been happening. That would be due to a special cause of variation. Key to understanding number 3 says, any special cause variation must be eliminated before one can attempt to narrow the range of common cause variation. Here are some examples of special causes of variation. An equipment malfunction caused occasional spikes in the sizes of holes drilled. An out-of-stock condition causes a customer order to be delayed. Or a vibration from passing trains causes chemical reactions to speed up. Or a temporarily opened window causes the temperature to drop. Or an untrained employee temporarily fills in. Until we can eliminate special cause variation, we don't have a process that we can improve. There are factors outside the process which affect it and that change the actual process in ways that we don't know. Once we know that we have special cause variation, we can use various root cause analysis methods to identify the special cause so that we can eliminate it. Only then can we use process or quality improvement methods like Lean Six Sigma to try to reduce the common cause variation. But how do we know if we have special cause variation? Key number 4 says control charts show variation in a time sequence from left to right. Control charts tell us whether the variation is within the prescribed range for common cause variation. There are a number of different types of control charts. These are described in the Part 2 video, Control Charts Part 2, Which to Use When. Run rules define whether the variation is random or whether there is a pattern, which also would be visible on a control chart. Most statistical software packages which produce control charts will also identify any patterns defined by run rules. How do we find the range of acceptable variation which distinguishes common cause variation from variation caused by a special cause? The defined range for common cause variation is generally 3 standard deviations above and below the center line, for example, the mean. The upper and lower boundaries of this range are called the upper control limit, UCL, and the lower control limit is the LCL. These limits are usually depicted as colored or dotted lines, horizontal lines. The center line is solid. If 0 is the lowest colored or dotted, if 0 is the lowest possible value, for example, when we're measuring time, a lower control limit calculated to be less than 0 is not shown. This chart plots the time in seconds that it took to complete a specific step in a manufacturing process. All the times except for the outlier at 28 seconds are between the lower control limit and the upper control limit. So they are due to common cause variation. But because of the one value outside the range, this process is not under control. We need to take a look at what may be the special cause of that anomaly and try to fix it. We just showed how control charts tell us whether the variation is within a range that indicates that the process is under control. The second requirement for a process to be under control is that any variation must be random. Sometimes a repeating pattern is obvious in the graph, but to be precise, we use run rules which define patterns, telling us whether the variation is random or not. There are a number of run rules, and some patterns are not always easy to spot by eyeballing charts. Fortunately, the same software which produces control charts will usually also identify patterns described by the run rules. Here are some of the common patterns which indicate non-random, that is special cause, variation. A trend of 6 or more consecutively increasing or 6 consecutively decreasing points. A shift in the mean, 8 or more consecutive points on the same side of the center line. Cycle, 14 or more consecutive points alternating up and down, or 2 out of 3 points beyond 2 standard deviations and on the same side of the center line, or 4 out of 5 points beyond 1 standard deviation and on the same side of the center. Or a line would be 15 or more consecutive points within 1 standard deviation of the center line. In the discipline of statistical process control, SPC, we collect a number of small samples in order to identify variation over time. The samples could be as small as 4 or 5, and we collect 25 or more of them. These are a special kind of samples called a rational subgroup. Rational subgroups are comprised of individual data points collected from a process under the same conditions. For example, the same step in the process, the same operator, the same machine, close together in time. So we can calculate a statistics, for example, the mean, the proportion, the standard deviation, or range, for each rational subgroup. It is the value of that statistic which gets plotted in the control chart. In the Part 2 video, we will cover these 7 different types of control charts and which to use when. These are the S chart, the X chart, which is also known as the individuals chart and also known as the I chart, the X bar chart, the NP chart, the P chart, the C chart, and the U chart. And that's it for this video. If you liked this video, please remember to press the thumbs up like button on your screen below. I'll be making more videos of some or most of the 60+ concepts in the book if folks like you tell me more videos are needed. Please subscribe to this channel to be notified when new videos are uploaded. Also, the website statisticsfromatoz.com has a listing of my available and planned videos. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job while studying or during an open book exam. For that, nothing beats a book or an ebook. You can also learn more about those on the website. I'd recommend following my blog at statisticsfromatoz.com/blog. I've got some things there that hopefully you will find interesting, like a statistics tip series, as well as posts showing that you're not alone if you're confused by statistics. I'll also be posting on the Facebook page Statistics from A to Z, and on Twitter is @StatsA to Z.